Hello everyone, my name is Farid Jidat. I am a PhD lead solution engineer within Altair. I am going to talk about the generalized projective method and show you how to make this generalized projective method, the creation of the support, computation of the forces, and show the arrow of the forces and the curves. Alright, so as you know, for the NVH coupling, we do have projective method based on Maxwell tensor, and then direct method for surface forces based on the virtual work method directly computed on the mesh and the mesh element of flux. So the forces here are perpendicular to the support. And there is also a method to compute Laplace forces or Lorentz forces. So we suggest for NVH coupling really to use simplified projective method when it's possible. And when it's not possible, in case of eccentricities or axial flux machine or a specific shape of the tooth that are not cylindrical, so generalized the projective method is more appropriate. We do have a lot of materials using a simplified method, and today I wanted to make the video and focus the video on generalized projective method. So first, let's see what is done in simplified method. Yeah, it is mandatory that the support should be cylindrical. So then what we need is really to import what we call the mechanical mesh on what we want to compute and project the magnetic forces. However, the magnetic pressure actually are computed in the air gap, and let's say we call it the virtual cylinder. So this virtual cylinder is automatically created by Flux and is not visible from the user. And then on this virtual cylinder, located between the sliding cylinder and the mechanical mesh, in our case, for instance, it is a mechanical mesh imported on the inner print of the tooth. Then in this virtual cylinder, we will compute the magnetic pressure and we will project them on the mechanical mesh imported in order to compute the magnetic forces. And this is using the Maxwell tensor. This is exactly the same thing we need to do in generalized projective method. The only difference here is that we need to create the computation support or the virtual support we have in the simplified method, which was created automatically, right? So this virtual support can be created in Flux or imported, like the mechanical mesh. The magnetic pressure will be computed on this virtual support and projected on the mechanical mesh imported. Okay, so today I am going to consider this example. This is a DC machine, a 3D project available from the examples from the supervisor. So this is a no-load test I launched. So there is no supply on the coils and there is only the cooking torque. Okay. To compute the magnetic forces and to go to export them, we need to go to the data exchange, open data exchange, and go to the context dedicated to mechanical coupling. So I will show you two ways to create the mechanical support and the virtual support. So let's import first the mechanical support on the stator. So if I go here, I'm going first to create the coordinate system. This one, which in meter, it's already created. And then I am going to import my stator mechanical mesh. and it is belonging to mechanical set stator, the fixed one. So it is imported, and actually it's not visible. And if you zoom, it is actually too small. Why? Uh, because it was in millimeter. That's why I created the coordinate system that I put in meter here. And then now if I change the coordinate system from the standard one to the one I created, then I will have my mechanical mesh here. Okay, so now I need to create a virtual support. So the virtual support I need is located, actually, if I put like this, it should be located between the mechanical mesh and the sliding cylinder. Or if you have not a sliding cylinder, you need to divide virtually the air gap to 4 layers and put the quarter close to the mechanical mesh actually. So here I am going to create directly the first method I am going to show you is directly creating the mechanical mesh through the faces plus an offset, right? So I will select the faces here. I will make it associated with a volume region as stator, and we'll put an offset here. Be careful, it's in meter, so I have to put dimension in. And I will let rebuild because I have a symmetry here. And let me call it virtual support stator. So this is the first method to create this virtual support. I will show you later on the rotor another method to create this virtual support. So let me make it visible. And as you can see, this is it. There is an offset of 0.025 millimeter. Okay. So now I have my support. I imported the mechanical mesh and the virtual support where I am going to compute the magnetic forces, and then I can now create the data collection. So data collection, it will be generalized projective method. I will select my mechanical mesh and my virtual support. If I want to compute, to convert the forces to radial and tangential forces, so you have to indicate that in the advanced way here. And so that the forces are, so the axis is parallel to OG. Yeah, I have to indicate the interval. In my case, I have a full mechanical period, so I can compute on the half. Okay, forces time on stator. Okay, then once I finish that, I can make evaluate or collect data. Here, once the data collection is finished, now I can go to data visualization and visualize the forces, not the harmonic yet. So I can visualize the forces on the computation I did, and I can show like this. Yeah. So this is the forces at this time step, but I can show the forces in another time step. Okay. I can show then the forces on the harmonics of the forces, and so I need to make the derivative now. Okay, let me hide the arrows and go to make a derivation of the data collection, make a new. For the derivation here, I can select, there is only one computation, and I computed for the half of the mechanical period. and then I can make automatic duplication. Okay, let me make harmonic here. I can validate, cancel, and then I have a right click and collect data. Once the data is collected, I can then go and visualize the harmonics now. So I can go to visualize the harmonic number 2, which is the fundamental actually, the mechanical fundamental in this view. And then I can and then I can really showcase these forces. Alright, then let me hide again this visualization and let me show you the other method to create the virtual support. So let me hide them, the first one I created. So the other method is using actually the grids. So the grids I want to create here are on the lateral grid for the rotor, and I want the top of the rotor and the bottom of the rotor, and this is actually what I am going to create. So these grids I have created them previously. I am going to recover only the Python command of it, and we'll create them here. So the grid I created is first the lateral grid, like here. And actually I need to modify it because it should be longer. Then I created another annular grid on the top. Annular. The first one is circular, and the third one is on the bottom, similar to the one on the top. So this is the grids here are to create and compute the magnetic pressure. So I will use them as a virtual support for the rotor. Please note that the grids are belonging to the rotor mechanical set. I am going to use these grids actually, but set defined of instead of defined of a set of faces, I am going to use defined by 2D grid. So I will call it virtual support rotor lateral. Okay. Here I don't need to rebuild the support actually, because the grid is actually cover all the rotor. Okay, so the mesh support, the virtual mesh support lateral is now created. Okay. Then I need to create a mesh support on the bottom and a mesh support on the top. Okay, so I will make the same thing, created by grid on the top. I will make rebuild the full device now, and will make on the bottom. Yeah, so this is the mesh support I created lateral and on the top and on the bottom. Please note that I put a high number of points on the lateral. Actually, we should make the same thing, high number on the top and the bottom as well, because we need to a higher number of points in the virtual support than the mechanical support to compute the magnetic pressure. So this is quite similar to what is done automatically actually inside the simplified method, which is not visible to the user. Okay, so now I have created this support, virtual support with the grid. Now I can again apply the projective generalized method. What is missing here is now the mechanical mesh on the rotor. So I have to go to data new support, make a new, and now I need to import the mesh. So I have to import the mesh on the mechanical support rotor. I will import it on the coordinate system I defined with the meter. Otherwise it will be too small. So this is depending on your actually mesh support from where you exported it. So you may need or not to create like I did coordinate system in meter or in millimeter. In my case now I need to import it on the rotor. So let me call it mechanical support rotor, and let's import it. So this is the mechanical mesh support rotor is the print of the outside tooth actually. Then now I can go to the force data collection, a new generalized projective method. I will select the rotor and then the support I created from the grid. So bottom, lateral, and top. I will make the same thing here, collect for half of the mechanical period. So this is a time computation, right? So let me force time and the rotor. And I can make OK now. But maybe I need to indicate I want them in the forces to be decomposed on radial and tangential first. And then I can go again and collect the data. Okay, now the force collection is finished. I can go to the data visualizer and force visualizer. I can now visualize the forces. Something interesting here is that previously I displayed for on the nodal. Now I can display the global force. It is possible because I have separate mechanical mesh for each tooth. I have one support. So I can show the global force, right? If I put it like this and make them a little bit. Yeah, so once I showed this global force, as I told you, maybe to make it more visible, I can hide this virtual support. And as you can see, this global force is computed on the barycenter of the mesh support of each tooth. Okay. What is interesting also is I can go to the data visualizer, results and curve on one point. Then I can make a standard data evolution curve, and maybe I can select this group or the other one. Let's select the first group, and I need to visualize the curve on the interval I used for the computation. Okay, so you can see here radial component, tangential component, z component, which is almost 0, and then you have the force, the, the, the module of the force. Okay, let's now make the derivative of these forces I computed on the rotor. So same thing, I have to go to derivative data collection, new, okay. I have to select the forces on the rotor. Previously I computed for half of mechanical period. Then I will make automatic duplication here also. So really the generalized projective method is different from the simplified one only on the virtual support. Simplified one is automatically created, and generalized projective one you need to create it yourself. Here, once I created this data collection for the derivation on the rotor, I have to collect data. Then it is done, and now I can go to the data visualizer again, and now I can show the harmonics on the rotor. So new, and I can go to data collection rotor and show the harmonic too. This is if I show it on the nodal, I can make the same thing on the rotor, but on the global and show the harmonic too. Then same thing, I have these forces rotating one. And as I did, I can, for the time variation of the forces, I can also visualize the force F50 of, like, let's say, this group 1. And the number of harmonics to display, let's put 50. Okay, then we can see this is a DC component, then we have the fundamental, and we can see the other interesting harmonics of the forces. Then once you check everything, you can go to data export and export the mechanical mesh with the forces, the FFT spectrum on each node of the mechanical mesh. Thank you for your attention, and please feel free to ask us to the support if you have any question. Thanks. Bye.